All right, 1.2 basics of functions and their graphs. This is really basic. I mean, whenever we talk about functions, a lot of the stuff today is really things that you had probably more in like Algebra 1 than you did anything. So we're going to touch on this pretty quick and then kind of go from there. It's more the stuff that's in 1.3 whenever it's the more functions or more info on functions, stuff like that, that you will get into things that you really haven't seen. Whenever you have like a definition of a relation is just basically an ordered pair. It doesn't have to be numerical. Okay, so like in the example down at the bottom, it says find the domain and the range of the relationship below, which shows a correspondence between highest paid TV celebrities and then their earnings. So like it's Oprah Winfrey is like 315 million. Simon Cowell is 80 million. I'm assuming that's Tim McGraw is 80 million. Ellen DeGeneres 55 million, and then Ryan Seacrest is 51 million. So, whenever we talk about the components and you have the domain and the range, for like whenever we graph and with functions, domain is always your x value or your input value. But in some cases, whenever it's not necessarily just numbers, when it's an actual relation, like in this case, Winfrey, Oprah, Simon Cowell, McGraw, Ellen DeGeneres, Ryan Seacrest, those would be your domain values because that's the first value. Okay? And then your range would be the second component, so like how much they make. Usually whenever we deal with domain and range, domain is usually going to be some sort of either category or it could be like time. Whereas usually your y value is going to be a numerical value in most cases. When we actually talk about the function, then it's going to deal with the first set being the domain, just like we've kind of already talked about whenever it's all numerical. Your first term is going to be your domain. Your second part is going to correspond with the range or the output. So like down at example 3, you have the relation of, or it says determine whether each relation is a function. So remember, for it to be a function, then you can't have repeating domain values that have different output values. So like on 3, your domain here is, your domain of your values are 1, 2, 3, and 4. Whereas your range is the 6, you have 6 again, and then 8, and then 9. This is okay. This is okay to be a function. It's when you can have repeating y values, okay, or range values, but you can't have repeating x values, okay, unless they have the same output. If you think about it, if you and somebody else work the same job and you both work 6 hours, you should get paid the same, right? There shouldn't be a different amount that gets output. Okay? So you can't have two values with the 6. Like 6 can't basically stack two values on top of each other. Okay? So my issue really isn't with the 8 and the 3 and the 9 and the 4. It's really right here. Okay? If I would actually plot this out, okay, I would have, a point at 6. It would keep going. Okay? Be 2 points basically stacked on top of each other. Do you remember whenever we deal with, and we'll talk about this in a minute, whenever when you actually physically graph things, what is it called? What does it have to pass to be a function? You remember? You remember what VLT stood for? Vertical line test, right? Okay, so you can't have two x values that repeat themselves, okay, and have different y values. Okay, you should never have, if we're dealing with domain and range, your domain should never have less values than your range. Okay, 1, 2, 3, and 4. I should never have more range values than I do domain values. I can always have more domain values than range values, or they could be the same, okay, the same amount, but I should never have, if there is less domain values than range values, then it should send up some sort of red flag. Then whenever we talk about functions as relations, or excuse me, as equations, then not every equation that you have with both x and y values are going to be functions. Okay, so basically what you want to do is you want to solve the equation for y and determine whether more than one value of y could be obtained for the given x. Okay, so like if I have 2x plus y is equal to 6, okay, if I solve for y, I'm just going to subtract 2x from both sides, and I'm going to have y equals negative 2x plus 6. Now, is this going to be a function? What kind of equation is this? Five's a function. Okay, it's a linear function. It's y equals mx plus b. Okay, it's a straight line. Whereas, what is, just looking at it, do you think 6 is a function? Rachel, you're shaking your head no. Why no? What is, so if we're solving for y, okay, if I'm going to solve for y, that means I'm going to subtract x squared from both sides, and I'm going to have y squared equals negative x squared plus 1. Then I would have to take the square root of both sides, and I would have y equals the square root of negative x squared plus 1. What is the problem? Okay, so it says determine whether more than one value of y could be obtained for a given x value. So basically, could I put in two different x values, or two of the same x values, and get various numbers? Okay, like if I put in two, if I plugged in 2 here, what's the problem if I plug in 2 for x? Like if I have y equals square root of negative 2 squared plus 1. Does anybody see an issue with negative 4 plus 1? Or the square root of negative 3? It's negative underneath the radical, right? Hey? What's the problem with that? It's going to be imaginary, right? What equation, and you may or may not know, okay? This looks, it's not exactly, but it looks fairly close to, it's not a circle because it's not minus, okay? But anytime that both values, your x and your y values, are squared, then you're most likely going to have some issues. Okay? That's going to give you some problems because there's really only one number that I can plug in that I'm not going to get a negative value. Or really, I guess there's really one set of values. Anything from that's over 1, I'm going to have issues, right? Okay, it's always going to be an imaginary number. Whereas if it's a fraction, then it's a little bit different, but I'm still going to have multiple values, because what happens whenever I take the square root of any number? I always have what? Positive and a negative, right? So no matter what, like if I have numbers between 0 and 1 that I plug in here, I'm going to get a positive and a negative value, okay, because I'm taking the square root. Whenever I have function notation, basically it's just evaluating problems. We're evaluating, the -5 is just going to go in every spot that there is an x. So if I'm going to solve, I'm going to have -5. I would put the whole thing underneath in a parenthesis. So -5 squared minus 2 times -5 plus 7. Okay, so 25 plus 10 plus 7. So with my equation, I'm going to have 35 plus 7, so 42. Even if, like on number 8, even if it is x plus 4. So for every x, I'm going to put in a parenthesis, I'm going to put x plus 4. So if I have x squared, that means I'm just going to go x plus 4 squared minus 2 times x plus 4. Okay, and then plus the 7. So no matter what I have inside that parenthesis, that whole thing is going to get replaced with wherever there's an x, that whole parenthesis is going to get replaced. Okay, or that x value is going to get replaced with that parenthesis. And then I would square the x plus 4. I would have x squared plus 8x plus 16 minus 2x minus 8 plus 7. And then we would just combine like terms and have x squared plus 6x plus 15. A and P pass the vertical line test, and then B and D will not, because basically it's just, if we hit more than one spot, or if we hit more than one, then it's not going to pass the vertical line test. Okay, so A and C are going to pass, B and D don't, because it hits more than one spot. And only other real thing that you had was, remember that if it's an open dot, that means it doesn't extend beyond that point. If it's a closed dot, then it basically just stops there and it belongs to the graph. If it's an open dot, then it indicates that the graph does not extend beyond that point. So basically it gets up, that point is not included. And then the arrow just means that it continues going indefinitely in that direction. So whether it be left, right, wherever, if it has the arrow, nothing new really in terms of that. So like here, it just talks about with HIV and how it kills helper T cells. And it just kind of goes, and this is various colors, obviously, but it's going to stop after 11 years, or at least that's where it starts at year 0. It kind of keeps going. Since it's closed, then you go from there. Just like we talked about yesterday, using the graph, basically to find various values. Like whenever x is 8. Okay, I'm going to go to 8 and go up and say that the average T cell count is probably right around 200. Okay, and then for what value of x is f of x equal to 350. So then I'm going to look at 350, or about where I think it is, and just kind of go from there. And I'm going to say probably close to about 6 years, maybe 5.5, 6. But again, it's kind of that educated guess as far as, since you don't have an actual function that goes with it, you've got to use a little bit of common sense to say, okay, this is